Hello everyone, we are in chapter 12, and in chapter 12 we're going to look at exponential functions and logarithmic functions. In this lecture we're going to take a look at section 12.1, which talks about composite functions and inverse functions. So that's the section that we're going to be talking about in this lecture. And for your homework we're going to go to pages 787 and page 788. So let me show you those pages. Page 787. Once this loads, you can see your homework from that page. And there it is. So let me scroll this down. And here you go. And this is the homework in that section on page 787. Okay, and you can take a look at the homework documents in Canvas in order to see which problems you're doing. I'll do ones like your homework problems. And on the next page you're doing, on page 788, I believe you're only doing one exercise from that page. And that's exercise number 63, I believe, which is section D, right in here. Graphing functions and their inverses. I believe you're doing number 63 is the one you're doing. I'll be doing number 64 with you. Okay, so there you go. And let's go with that to my notebook and we'll begin this section. So again, the title of the chapter is Exponential and Logarithmic Equations. In section 12.1, we're going to talk about composite functions and inverse functions. Now, this is a rather long section, so you might want to watch this section maybe with a break or just like a short recess, because I think it may actually run for almost 40 to 45 minutes to 50 minutes, something like that. Anyway, so let's proceed. Now here, before we actually talk about composite functions, I have made up an example. And in this example, we actually have two functions. So I have this first function, which is n equals 40 times x. Okay, this looks like an equation. N equals 40x. Now here, n is the number of t-shirts. Okay, and x is the number of employees. So 40x gives you the number of t-shirts. That's assuming, let's say, each employee is capable of making 40 t-shirts. This could be in a week, in a month, whatever this might be. So 40x will give you the total number of t-shirts. And then the function below it, this p, stands for profit. The profit is 15n minus 1200. So remember, n is the number of t-shirts. So you can think of this as if they sell each t-shirt for $15 and they subtract the cost, $1,200. Let's say this is a monthly cost. And these would be monthly productions then. And the profit would be in dollars. So here we have two functions. I'm just trying to illustrate the concept of function composition with this example. Now, if we take a look at an example, let's say I have 10 employees. Well, these 10 employees can produce n number of t-shirts. Each can produce 40 t-shirts. So 40 times 10 makes 400 t-shirts. Now, how much is the profit for producing 400 t-shirts and selling them, of course? The profit is going to be 15 times 400 minus 1200. That's $4,800. Okay, so it's pretty straightforward, no big deal. Now, what I've done here, I've actually drawn a couple of what we call function machines. So here I have one machine, the first machine, this is the second machine. And what I've done here is I've illustrated what we've done up here, this simple two lines. I have tried to summarize them using these two function machines. So in this function machine, n, the input is the number of employees, x10. So this machine multiplies x times 40 and outputs n 400, right? That's 400 t-shirts. And that in turn, that output is input into another function machine. So the output from the first machine becomes an input into the second function machine. And then the second machine will do 15 times n, so that's 15 times 400 minus 1200, and will output 4800. Again, this is exactly what's up here. I just put it in a schematic for you. Now, in general, this is what's going on with this problem. Through the first function, right, we're going to feed the number of employees, and then this function processes that information, outputs the number of teachers, the number of teachers go in, and outputs the profit. Okay? Again, pretty simple process. Now, let's take a look at what we just saw with the number of teachers. Here's another drawing again. So I'm trying to reinforce what's up here, what I've drawn up here. So again, number of employees, X goes in, multiplies by 40, output is number of teachers, 40x, n goes in, 40x plugs in for n, 15 times that becomes 600x minus 1200. This time out comes 600x minus 12. Now something subtle just happened here, and that's what I have in highlighted. Note, what goes in is the number of employees here. And the equation in the end, or the function in the end, actually gives you the profit as the number of employees, as a function of employees. It's not a function of number of t-shirts. So that's what's different from what was up here. See up here, 15n minus 1200, n, number of teachers, is input into this function, and that's how we calculate the profit. So this is the whole idea of function composition, is that we can actually express a final function in terms of the original input values. Okay, so here's the function composition now using the notation. I have x as an input, goes into g processes it, out comes the output, g of x. G of x goes into this machine, f processes it, and out comes f of g of x. Okay, so this is a new notation now. What I have here, that's a new notation for us. The output of a function composition would be this, what seems to be nested functions. So what I have here, the sketch here, is the composition of two functions, f and g again. That's what that is. Now, how do we write the way we have chained or linked these functions? Because we process through g first, f second. So we're going to write this as f. And then in the book, and most math textbooks, almost all of them, they use the circle notation. So this is f circle g. It looks like fog, but it's f open circle g. And this is f of g of x. But this is how we write it in order to understand it. This is just a notation, and this is how to write it to understand it. Okay? Okay. And the way we read this is f of g of x. That's how it's written. That's how it's read. So it's written as f parentheses g parentheses x close paren, and we read it as f of g of x. So function composition is nothing but linking different functions together or chaining them together. We can chain or link several functions together. So I can link f with g, then g with h, h with I, and so on. And in that case, I will have f of g of h of I of j of k of l, and so on. Depends on how many layers of composition is necessary. Okay. So that's what the function composition is. Now, a few notes here that I have. Okay, our first note is this one right here. The function, the composition g of f of x, which is written as g parentheses f of x here, close parentheses. This is a different composition than the one above it. Okay, so g of f of x, f of g of x, they're not necessarily the same. And there you go. That's what that is. So I just want to show you in the first note that we could have a different order of composition here. So we don't have to have f of g of x, we could have g of f of x. That's when we switch the order of composition. So think of it as switching these machines. Putting f first, processing something through f, then feeding it into g. That's what the g of f is. Now our second note here, this one, and this is just to show you again how we can perceive these functions, function compositions as. If we have f of g of x, oftentimes we refer to g of x as the inside function, right? That's the function that's on the inside. And sorry, that's the function on the inside. And f is the outside function. So we have outside and then we have inside. G is nested within f, inside of f. Right next to that, we have g equal f of x. So f of x is the inside function, and this time g is the outside function. And what I have here, my final note right here, is that in general, again, what I said earlier, the composition is not commutative. Function composition is not commutative. So f of g, g of f would be a whole different composition, different outputs in the end. Now, let's take a look at an example on page 787 of your textbook. This is exercise number 12. So we are given two functions, f of x and g of x. So f of x is 3x squared plus 4, and g of x is 4x minus 1. Okay. Now, here is part A and B. In part A, the question asks to do f of g of 1. Okay, f of g of 1. And I'm looking at right here. F of g of 1. So first I'm going to rewrite, instead of the circle notation, I'm going to write it in a notation I understand it using the parentheses. So this is f of g of 1. And note, by the way, I'm using different colors for x here. For f, I'm using red. For g, I'm using blue. I'm hoping this will help you understand further on down what's going on with the composition, hopefully. So anyway, this blue 1, this is what goes into g. Now remember, the task of g is to multiply input x by 4, subtract 1 from it. So that's what this does. It does 4 times 1 minus 1, and that is going to evaluate to a 3. And then f of 3, that means now you look at function f and plug in a 3 in for x. So there you go. Wherever there is a red x, you're going to put a 3. So here's the only place there is a red x. So I'm going to put a 3 here. That's 3 times 3 squared plus 4. That's the next step, and the answer is 31. Now, in part B, we want to do g of f of 1. So again, I wrote it in a notation that I understand what to do with. And then we always work compositions from inside out. Keep that in mind, please, from inside out. So I'm going to work the inside first. That would be putting in a 1 in for f. And I did. That's 3 times 1 squared plus 4. And this evaluates to a 7. And then we plug in a 7 for g and do the arithmetic. Let's remember, in g, what g does, g multiplies its input by 4 minus 1. So I did 7 times 4 minus 1, and I got 27. And as you can see, there are two different results. So f of g of 1, g of f of 1 are not the same. Now in part C and D, notice we just have x's. We don't have a number to put in. So this is good for any x now, not just for 1. And we will use C and D just to show you how we could do part A using part C. Okay? But in part C and D, we're going to keep them general. We don't have a specific number to plug in. So f of g of x, that would be f of g of x. Again, I've written it in the notation I understand it. G of x, the inside function, is 4x minus 1. So I plugged in 4x minus 1 here. Then this is fed into f. And the function f again does 3 times x squared plus 4. So this is the input that goes into f. Now here I square the binomial. Remember, when you square the binomial, you do the first term squared, second term squared, that's this one, and then you do twice first by second. That's 2 times 4x minus 1 is negative 8x. You can also set this one up as FOIL and do FOIL with it to make sure you get this trinomial. In the next step, I distributed the 3 to within parentheses and combined like terms. 3 and 4 made 7. And there you go, that's f of g of x. Now g of f of x, similarly, that's g outside function, f inside function. So I plugged in f of x, 3x squared plus 4. This is what goes into g and replaces the x that's in g. Remember g, the instruction to g was 4x squared minus 1. It's up here. You see that? Right up here. 4x minus 1. So this is the input into g, so I'm going to plug that in for x. And so it's 4x minus 1. Distribute, combine like terms, and you get the results here. And again, as you can see, you get 2 different outcomes. These 2 answers are different because you have different composition. Now in part C, let's do part A using part C. Remember, in part A, the composition take a specific input of 1. So here's what this f of g of x in part C is good for. F of x, let's see, hold on, I guess I didn't do that. I could have done, okay, well, let me do that now. I thought I had done that. Okay, so we're going to do part A using part C, f of g of 1. So in here, if I want to do f of g of 1, I just plug in a 1 for x. That's 48 times 1 squared negative 24 times 1 plus 7. Now 48 times 1 is 48, negative 24 plus 7. Let's see, 48 and 7, that's 55. 55 minus 24, that's 31, right? And there you go. Notice the result here is 31, which is exactly the same as the result up there. The difference is once we have the general form of the composition, we can just look at plugging into the composition and look at the final output. You don't care about the in-between stuff. And this is all the in-between stuff that we don't care about. Let's take a look at another example. This next example is exercise number 19. Okay, and in exercise number 19, this one, again, is the same idea. F of x is x squared plus 4. G of x is root x minus 1. We still want to do f of g of 1. So here's f inside function g of x. So we plugged in a 1 in for x, simplified it, got 0, and then plug in a 0 into f, which is x squared plus 4. That's 0 squared plus 4, I got 4. In part B, the composition g of f of 1, this is the outside function, this one the inside function. I plugged in a 1 for f, for x into f. F squares x adds 4. So I squared it plus 4, I got 5. And then the square root of 5 minus 1. Now I'm going to g, which takes the square root of input minus 1. And that's input 5 minus 1, the answer is 2. So the answer to part A is 4, the answer to part B is 2. And I believe I have them in highlighted because we're going to verify, excuse me, we can verify those from part C and D. Okay, in part C and D, we keep them general. So f of g of x, that's f of g of x. Now g of x was root x minus 1. Plug this whole thing into function f. Remember, f will square and then add 4. Square root of x minus 1 squared is x minus 1 plus 4 makes x plus 3. And there's the answer to the composition. To try it with part A, I put in the 1 in for x, and I got 1 plus 3, 4. Notice how fast you get the answer here. And just like up here, that's not bad either. Okay, and then in part D, the same thing. g of f of x, that's g f of x inside function is x squared plus 4. And then that goes into g. Remember, g will take square root of x minus 1. This is like the x now. Takes that minus 1, and this is the final output. I redid part B, g of f of 1, where I just plug in a 1 here for x. And you get 1 squared plus 3, 4 square root of that is 2. And that is all with function compositions we want to talk about. So hopefully you followed what we've done so far. Okay, now let's talk about one-to-one functions. Again, I did mention this is rather long sections, but we'll make it through. So let's talk about one-to-one functions. Now, for this segment, what I've done is this. There are different ways we can illustrate functions. We can use function machines and the whole idea of input-output to illustrate the concept of a function. We can use mappings, or we can use ordered pairs. And this is what I'm doing. I'm using the ordered pair definition of a function. So, now remember, this is review. Hopefully, I know it's probably been a while. You may have forgotten this, but anyway, I'll explain things, what I'm doing here. Now, a function is an ordered pair. That's what this is. An ordered pair is a pair x comma y. And order matters, x first, y second. So, in this set, I have these made up random ordered pairs. So as long as you have one of those, you have a relation, actually, a relation. Now, a function is a relation, means a set with ordered pairs in it. It's a relation in which the first numbers are different. So these must be different in order to have a function. So in my example, 1, 2, 4, those are different numbers, therefore this is a function. Now, one thing if you note here is that 3 here and 3 here, these, on purpose, I made them to be the same. But nevertheless, nonetheless, the function f is a function. So what's important is that the first numbers must be different. The second numbers may not be the same. Now, and then I have made up another function g here. This function g directly below f. This one is 0, 5, 4, 7, 3, 11. Now for this one, again, the first numbers are different, so that qualifies it as a function. And this time I made the second numbers. See, I have these green dots above them. These numbers are different. So again, both of them are functions. However, the one that's g, because not only the first but second numbers are different, is what we call a one-to-one function. So the definition of a one-to-one function is this. A function is one-to-one if not only the x values, the first components of the ordered pairs are different, but so are the y values. So again, I brought these f and g down here again, and I'm talking about them now. In function f, because you have 3 here and 3, those are the same. Therefore, this function, again, it is a function, but it's not one-to-one. G, on the other hand, is also a function, but then now 5, 7, 11. Those are different. So because the outputs, the y's are different, therefore this function is indeed a one-to-one function. There you go. That's what this one is. This one is one-to-one, whereas this one is not, because these two elements, these two, are the same. Okay. Now, if we have the graph of a function, we can actually determine whether the graph of this function represents a function that is one-to-one or not, or just the graph of any equation, if the graph represents a one-to-one function or not. Okay, now here, how we do this is, in the book they call it the horizontal line test. So the idea of horizontal line test is this. Suppose I have a function, which I have here. My first one is this one. Suppose I have a function here I just made up. If I draw horizontal lines, that's what the blue lines are. If I draw these horizontal lines, these horizontal lines are going to cross the graph of the function at one and only one point. So this graph represents a function that is one-to-one. This one, well, this graph does not represent a function because it fails the vertical line test. Now I know we're doing horizontal line tests. Remember, horizontal line test is to determine whether the function is one-to-one or not. See, that's what it's used for. The vertical line test we do to determine whether the graph represents a function. And because the vertical line in this case crosses this curve at two places, so this is not even a function what I've drawn. So if it's not a function, then it doesn't make sense to do a horizontal line test for it. The prerequisite is you gotta have a function. So the horizontal line test here doesn't apply. Now if you look at this other one I have, this the parabola down here, this one, actually the graph of this inverted parabola is going to represent a function that is not one-to-one. Again, it is a function, but it's not one-to-one because it crosses at more than 1 point. Now, what's the big deal about this? Why do we want functions to be one-to-one? Because of the next idea. We're almost nearing the end of the section, by the way. So, in this next idea, you're going to talk about the inverse functions. So, if a function is one-to-one, remember that is a prerequisite for every one-to-one function. That's why it's so important to have functions that are one-to-one, so we can do this with them. Otherwise, we cannot even do it. But if the function is one-to-one, it has an inverse. That's a good thing actually to have. So how do we actually find this inverse? It's pretty simple. We do it by exchanging or interchanging the x and y values. That's how it's done. So I've made up an example again for us. So in this example, function f is ordered pairs 2, 5, 0, 3, negative 1, 7. And I'm using colors for a reason here. Okay. Now the inverse function, by definition of what is up here, the inverse function, again, is going to be right in here. The inverse is when we interchange the x and the y. So we just flip the 2 and the 5. See, 5 comes here, 2 goes here. Flip 0, 3, we get 3, 0. Flip negative 1, 7, we get 7, negative 1. And there you have it. Okay. And that's going to be the inverse function. Now, if we think about the domain and range of these two functions, this is interesting. Domain of function f, this first function. Remember, domain is the set of all x's, the first numbers. These are the blue numbers, 2, 0, negative 1. There you have it. What's the range of the function? The range of the function are the set of second numbers, the red numbers, 5, 3, 7. Now, if you look at the domain of the inverse function, this function, the second function, this one, the inverse function. The domain of the inverse function, set of first numbers are 5, 3, 7, and the range of f inverse is 2, 0, negative 1. And there you go. So looks like, and it is true, and no surprise because the way we define the inverse function. So it looks as if we actually switched these numbers, and the effect of exchanging or interchanging xy is to swap out the domain of the function with the range, so of the inverse. So in general, domain of a function is the same as the range of its inverse, and vice versa. Now, one thing I have done here, by the way, I've used this notation without telling you, right up here. This is a poor choice of notation rather, but it's pretty universal. All math books use it. This is actually the inverse notation. So it's f and then superscript negative 1. The superscript means inverse. Okay, so please do not confuse this with a negative exponent. That's why I called it a superscript. And here's what I mean. when we write f inverse, we do not mean 1 over f. We're not thinking a negative exponent rule. It is a poor choice of notation, but it is what it is. That's, again, pretty universal. All textbooks use that notation. Now, here I just pose a question like, okay, well, what's the big deal of this? Why do we even need to have an inverse function? And the answer you can see below it. The answer is simple. If we didn't have the inverse function, we would not be able to go back from output to input. Remember, the function usually have an input, outcomes and output, right? That's how we always worked with them. Well, sometimes you may see an output and we want to go back and see what was the input that produced the output. Well, you can do that if the function is 1-to-1. And here's what I've done for you. So, if you actually look at what I have here, this is the mapping, the idea of mapping with functions. So right in here, I have created a function that is 1-to-1. So element A corresponds with C, B corresponds with D. Now, in blue, A corresponds to C, okay, through function f. Now, the return path, if I want to go from C back to A, that has to be done through the inverse function. So you see, this way we have what I call a two-way communication between the elements of one set and the other set, right? So this would be your input, and this is your output. So we can actually communicate, the elements can communicate back and forth with one another. Now, the mapping I have on the left side, this is a function that is not 1-to-1, right? It's not 1-to-1. And, oops, I didn't want to do that. Okay, so this function is not, I'm not sure why am I doing this, sorry folks. So this one is not 1-to-1. I was going to use my highlighter and it wasn't, there you go. So it's not 1-to-1, okay. And you can see why it's not 1-to-1, because see, you have the same y, two y value, is same y value for two different x values. That's why it's not 1-to-1. But more importantly, here's what the trouble is. In this mapping, here's what I have. So I have 4 people. It's me and you, him and her. And then on the other side, him, his information maps onto his account. Let's say on this side, the output side are accounts, could be email accounts. Okay, so him, he maps onto his account. Her also corresponds to her account. So him maps onto his stuff. With her, she can go to her stuff. So okay, him and his and hers. Now, this is me and you. Let's say if this function is not 1-to-1, which is not, we're going to send information to the other side. I'm going to send my information. You're going to send your information to the same location. This could be, let's say, a server on the other side, okay? Let's say I put in my login ID, you put your login ID, and somehow they end up going to the same location on the server. Now, when it's time to communicate back with us from the server, let's say, from our account, if our account wants to find us and send us information, see right in here now, there's a dilemma. Who's going to receive this information? Is the information going to be sent to me? It's about me, and the information is about you. How does it know which way the return path is? So that's why it's important for the function to be 1-to-1, so we have a clear channel of communication like the drawing on the right side. Okay. Now, how do we find this inverse function? In order to find the inverse function, it involves two-step process. Step 1, by definition of inverse, remember that's when we switch or swap the x and the y's. So this is from the definition of the inverse. Right, that's what this is. And I did. So I swapped out x over here, y becomes x becomes y. Now this is what we call the implicit form of the function. Implicit form means you don't have y isolated. Okay, so x is equal to 3y plus 7. Now the next step here is to solve for y. So how are we going to solve for y? You want to isolate it. I'm going to subtract 7 and divide by 3, and I did. And this is what we call the explicit form of inverse function. See, when it's just y by itself. We have implicit again, where x and y is not solved, and explicit form is when y is solved. Implicit, y not solved. Explicit, y is solved. And at this point, I'm going to use the inverse notation, and that's what I did here. So in this step, I actually use the inverse notation. It's the same thing that I have directly above this line, right? It's the same information here. I just use inverse notation. And there you have it. Look at another example. In this next example, y is equal to, call it g of x, 2x minus 3. We want to find the inverse. So remember the two-step. We have swap and solve. Swap and solve. Or switch and solve. So step 1, we're going to switch the x and the y. So y becomes x, x becomes y. Again, this is the inverse. At this point, we have the inverse, the equation for the inverse. But we would like to solve it for y, and we do, and this is what we get. To solve for y, everybody I'm sure can do this, right? You add 3 to both sides, or move negative 3 to the other side, divide by 2, and this is what you get. So, in turn, we have solved the equation for y. This is the explicit form. And let's look at another exercise, number 58. We want to do the same thing. And you can kind of see this one. F of x is root x minus 1. We want to find the inverse. So we're going to switch the x and the y. Solve for y. How do I solve for y? Because it's in the radical square root, we're going to square both sides. Remember the principle of the power property or principle of equations. I'm going to raise both sides to the second power, square both sides. Squaring a square root will get rid of the radical. We'll get rid of the square root, which just gives you the radicand. And then we can solve for y. Simple. Add 1 to both sides, and this is the inverse function. Okay. Now, finally, and we're done with this one. Okay. It turns out that the graphs of every function and its inverse, and of course we're talking about every function that has an inverse, right? So we're talking about functions that are, in this case, every one-to-one function. But, that's kind of implied here. The graph of every one-to-one function and its inverse are symmetric about the line y equal x. Okay, so in example number 64, exercise 64, again, I believe you do number 63. The question is asking to actually graph the function and its inverse. Okay, so first we're going to find the inverse. And here's the inverse, pretty easy, right? Two-step, switch and solve. So I switch the x and the y, right? Y becomes x, x becomes y. And then you solve for y, means you isolate y. And here I added 1 and took the cube root of both sides. And that's how I got the equation for y. And then I use the inverse notation, and here's the equation for the inverse function. Now the graph of these, I took the easy way out. I actually graphed it with the software. Now, just to kind of point this out, because you may have this on your exam, the graph of x cubed in general, this is what x cubed looks like. X cubed. And this part of it goes down like that. Just so you know, this is what the general form of the graph of x cubed is. Now, the blue curve is x cubed minus 1. So if you take this basic x cubed graph and drop it 1 unit, you're gonna get this right in here. You're gonna get this blue curve. Okay. Now this other one, this you don't graph this one. Actually, I had to find the inverse in order to get the software to graph it. But you can actually do this by reflection. Again, what we set up here is that the graph of every one-to-one function and its inverse are symmetric about, right? When we say that the graphs are symmetric, right in here, and they're symmetric about the line y equal x, it really means what you're seeing here. So at this point, the way to do this, if I really want to do it, say by hand without going through the inverse, so you draw this 45-degree angle line, that's y equal x, and then we actually use reflections. So remember, the blue curve is x cubed minus 1. So here's 1 point, right? This point is 0, negative 1. When you switch or swap 0, negative 1, you're going to get negative 1, 0. So that's going to be a point on the graph of its inverse. Again, that's without knowing even what this green function looks like. You can cover this up. We don't even need it. Look at this point. This point is 1, 0. The reflection of that would be 0, 1. It's right here. And this point, which is a point on the line, there is no reflection. So here I have again 1, 2, 3 points, right? True, right in here. 1, 2, 3 points. And I can connect these dots together. I'm going to use the blue curve. Actually, I'm using green just to be consistent. And you can actually draw like that, and that's how you get the graph of the inverse. And just keep on going. And then, for example, the reflection of this point will be right here. The reflection of this point will be here. And then you can draw this other portion, the lower portion of the inverse. So you don't really need to know how to graph the cube root of x plus 1. This is how they want you to do anyway. They want you to reflect it about this line x, y equal x. Okay, so we're done. Again, sorry, I know it's kind of a long section, huh? But we covered a lot of grounds. Now, what's interesting is this, folks. The title of this chapter was, what, exponential and logarithmic equations, right? No mention of those at all. Everything we've done here has to do with one-to-one function. So what we just went through has nothing to do with exponential and logarithmic functions. Okay, this is true for all one-to-one functions, what we just did. Now in section 12.2 later on, that would be the other lecture I'll do, we actually talk about exponential functions. And then in section 12.3, I believe, is when we talk about the logarithmic functions. And it turns out that those two functions are inverses of one another. That's why we had to go through this whole discussion of inverse functions. So we're prepared for those two functions. Okay, so with that, we are done with section 12.1, and hope you followed everything we did today.